Let's talk a little bit about congruence. So first, our definition. Let m be a positive integer with m not equal to 1. Two integers a and b are congruent modulo m if and only if the difference b minus a is divisible by m. For instance, 1 and 7 are congruent modulo 6. That is because if you find the difference of 7 and 1, 7 minus 1, you get 6. And 6 is divisible by 6. The integers 1 and 13 are also congruent modulo 6. Why? Well, 13 minus 1 equals 12, which is divisible by 6. 5 and 29 are also congruent modulo 6 because 29 minus 5, which is 24, is divisible by 6. Let's look at some notation. We use A is congruent to B mod M to denote that A and B are congruent modulo M. So for instance, in our previous examples, we have that 1 is congruent to 7 mod 6. We also had that 1 is congruent to 13 mod 6, and 5 is congruent to 29 mod 6. Now the way you pronounce this, you could say it this way: A is congruent to B mod M, or you can just pronounce it thoroughly. You could say A is congruent to B modulo M. That's how you pronounce that notation. You have it. Next, let's talk about different ways of expressing that two integers are congruent modulo m. So let m be a positive integer with m not equal to 1. Equivalent ways of expressing that two integers a and b are congruent modulo m are. Well, we have that if we state that b minus a is divisible by m, that is equivalent to saying that a and b are congruent modulo m. Why? That's precisely the definition of a and b being congruent modulo m. It is a consequence that if b minus a is divisible by m, it is an algebraic consequence that a minus b is also divisible by m. So if b minus a is divisible by m, mathematically you will say it this way: if b minus a is equal to k1 times m, where k1 is some integer, then you could conclude that a minus b is also an integer times m. All you have to do is change the sign. So you have a minus b equals to negative k1m. This is, if this is true, this follows. Just multiply both sides by negative 1. So saying that a minus b is divisible by m is equivalent to saying that the a and b are congruent modulo m. This is another way of saying that. This is simply our notation, the notation we just introduced. If we write a is congruent to b mod m, that is simply stating the fact that a and b are congruent modulo m via our notation. Notice that if you change the order to b is congruent to a mod m, you're saying exactly the same thing as that. Just use this equivalence here. This and that are the same statement. So saying that B is congruent to A mod M is equivalent to saying that A is congruent to B mod M. Another way of saying that A and B are congruent mod M is by saying that B minus A is a multiple of M, because being a multiple of M is the same as being divisible by M. Another equivalent way of saying that A and B are congruent mod M is by saying A minus B is a multiple of M. You just exchange the roles here and use property 2 in this list. So let's skip these equivalent ways of expressing that A and B are congruent modulo M so that we can use them when needed. Alright, some terminology. Let M be a positive integer with M not equal to 1. To reduce an integer A modulo M means to find the remainder when dividing A by M. So, quick example. To reduce 16 modulo 3 would mean to find the remainder when dividing 16 by 3. Well, not very complicated. If you take 16 and you divide it by 3, you will get a remainder of 1. So to reduce 16 modulo 3 means to find that remainder. Here's a consequence of here's a direct consequence of division. If you have that A reduced modulo M is R, then two things you know. Number one, that R is a number between 0 and M minus 1, because if it's a remainder, it's between 0 and 1 less than the divisor. And another consequence is that A is congruent to R mod M. Those two are consequences of what it means to reduce A modulo M. Let's look at one example. Reduce this big number, modulo 13. The big number happens to be 894,761,987. So we want to reduce this big integer modulo 13. Then what we want to do is we want to find the remainder when dividing this number by 13. A very direct way of dealing with this problem is to actually perform the division, perform the long division in this case, of 894,761,987 divided by 13. So you perform your long division, you perform your division process, and down here you will get your remainder. So when you reduce this big number, 894 million and change, modulo 13, you obtain 2. By the way, this would take maybe a few minutes to complete, maybe 2 or 3 minutes. But you will get an answer. It's a very direct way of solving the problem. So therefore, 894,761,987 reduced modulo 13 is 2. You can write it using congruence notation. Note the following. It is, while the question of reducing an integer A modulo M is a straightforward one, the long division approach could be unfeasible. For instance, if we want to reduce 2 to the power 100 modulo 21, using long division, this would be a rather overwhelming task to do this. For one, you have to find the 2 to the 100. That is an extremely big number. So what we want to do now is we're going to proceed to identify some properties of congruence that will make this problem a relatively simple one in comparison to long division. So let's proceed to list some of the properties. Alright, so here are some properties of congruence. Let's begin with m being a positive integer and not equal to 1. First property in this list is that the relation consisting of ordered pairs that are integer pairs such that A is congruent to B mod M, that relation, that set of ordered pairs is an equivalence relation. What is an equivalence relation? Here is a reminder of what that was. If you call this relation R, so one property that needs to be satisfied to have an equivalence relation is that if A is an integer, A comma A is in the relation itself. Also, if we know an ordered pair belongs to R, so if there is an ordered pair A comma B that belongs to this relation, then its inverse will be there as well. So B comma A also belongs to that relation. So that's a property. And the third one is if A comma B belongs to the relation and B comma C belongs to the relation, then A comma C belongs to the relation. So this relation right here, defined as the set of ordered pairs AB, which are integer ordered pairs, such that A is congruent to B mod M, this relation is an equivalence relation. Another property. If A is congruent to B mod M and C is congruent to D mod M, then their sum, the sum of A and C, will be congruent to the sum of B and D. Similarly, for their difference, A minus C will be congruent to B minus D. So we're summarizing both results in using this notation. If A is congruent to B and C is congruent to D, then A plus or minus C is congruent to B plus or minus D, where you of course will write the correspondence according to the order of the signs. Another property is if A is congruent to B mod M and C is congruent to D mod M, then the product of A and C is congruent to the product of B and D mod M. If K is a positive integer and A is congruent to B mod M, then A to the power K is congruent to B to the power K mod M. That's here another property of congruences. There is supposed to be some analogy to equality in here. The audience may recall that if A equals B and C equals D, then if you add both sides of the equation, A plus C you get equality. So A plus C is the same as B plus D. If it's minus you're doing, if it's subtraction you're performing, then similarly the property of equality applies. So this our second congruence property is an analogy to this property of equality. The third one will be A multiplied by C equaling B times D. So that's the property of equality. This is the analogous property for congruence. Finally, if you have A equals B, then if you raise both sides to the same power, you still get equality. So there is some sort of a parallel between these congruence properties and some of the familiar properties of equality. Now, in this presentation, we're going to go ahead and prove items 2, 3, and 4. We leave one as an exercise for the audience. In item 4, we will prove the statement. We will use an algebraic identity, which will be left for the audience to establish. So let's do number 2. Let's prove number 2. So our hypothesis, so proof of 2. So let's write down our hypothesis. First, we're assuming that A is congruent to B, and we're also assuming that the C is congruent to D. Okay, so here is our goal. We want to show that A plus C is congruent to B plus D. Let me try that again. So here is our goal. A plus C is congruent to B plus D mod M. We also want to establish that A minus C is congruent to B minus D. That's our goal. So let's try it. Oh, what does that mean? What does A congruent B mod mean? Mod N means? It means that B minus A is divisible by M. Oh, that's the same as saying B minus A is K1 times M for some integer K1. Similarly, C is congruent to D mod M means that D minus C is a multiple of M, so we're going to call it K2M for some integer K2. Let's do the following. In this equation right here, let's add them. If you add them up, what do we get? We're going to get B minus A, B minus A, plus D minus C equals to K1M plus K2M. K1M plus K2M. Notice that our goal would have to, if we're doing the addition part, our goal is that B plus D minus A plus C be a multiple of M. Are we going to get that? Well, let's notice that negative A minus C, you can factor out the negative and be left with A plus C. So we got that part of the goal. Now, realizing that this is a multiple of M, it's just a matter of factoring out the M. Okay, so we've got one of our goals accomplished. We have that a plus c minus, excuse me, we have that b plus d minus a plus c is a multiple of m. So that's just the same as saying that a plus c is congruent to b plus d. Mod m. So we've got the plus part right now. Realizing the minus part is just going back to our original equalities instead of doing addition, subtraction. Do subtraction. So let's try that out. So we're going to do this one, get rid of it. Subtract the second equation from the first one. So what do we get? On the left hand side we have b minus a minus d plus c equals to k1m minus k2m. Notice that on the right hand side we can factor out the m as we did before. On the left hand side, let's see, we're going to get the b minus d minus, now we should take negative a plus c and factor out the negative, so you will get minus a minus c. Notice, negative a plus c, so it matches. So what does this mean? This means that b minus d minus a minus c is a multiple of m. What does that translate into in terms of congruence? That translates into the following. A minus c is congruent to b minus d mod m. That takes care of the second half. A minus c is congruent to b minus d mod m. Alright, let's try now proving property 3. Property 3 says that if a is congruent to b mod m and c is congruent to d mod m, then a times c is congruent to b d mod m. Proof of 3. So here is our hypothesis. A is congruent to b mod m, c is congruent to d mod m. Our goal is to show that, so our goal is to establish that a multiplied by c is congruent to b multiplied by d. C is congruent to b d mod m. Let's start by writing down what each of these two mean. So we have b minus a is equal to k1m for some integer k1. From the second one, d minus c equals to k2m for some integer k2. Let's do the following. Let's multiply both of these equations. Multiply them. On the left hand side, we're going to get b minus a times d minus c. On the right hand side, we're going to get k1 times k2 m squared. Because m times m is m squared. Distribute, you have b d minus bc minus ad. Negative times negative is positive plus ac equaling k1 k2 m to the second. our goal, if you think about what it means that BD minus AC is a multiple of M. That's what our goal is. So I have the BD part, but I don't have the minus AC right now. So let's do this. Let's introduce it. So you have a BD. Let's introduce the minus AC part. But if you're going to subtract it, make sure you put it back. Minus AC plus AC. This is a small manipulation here that allows you to get part of the goal. You want to see what BD minus AC turns out to be. Is it going to be a multiple of M? Well, let's see. Let's solve for it. So you have BD minus AC. Now, send everything else to the other side. So on the other side you have K1, K2, M squared. Now when you move this to the other side, you're going to get plus BC minus AC. And you're going to get plus AD minus AC. Notice that in this first pair right here, in the middle pair, you can factor out this C to get B minus A, C. In the last pair, you can factor out the A. So A, B minus C. Now note, recall that B minus A is already a multiple of M. Also recall that D minus C is also a multiple of M. So what you could do is rewrite them as multiples of M. So that's a K1 M times C. That's A times K2M. So one last step. Notice that these three terms, K1, K2, M squared, plus K1 MC, plus A K2M, they all have M in common. So you can factor out the M. And there you have it. BD minus AC, BD minus AC equals a multiple of M. Let's just write down what's left after you factor out the M. You get K1, K2M, K1, K2M, plus K1C, plus A K2. So goal accomplished. All right, property 4. Property 4, we are going to let K be a positive integer and A be congruent to B. So you have A is congruent to B and K is a positive integer. Now, let's write down what the goal is and realize that it will be relatively simple to reach it. If we have a way of expressing our goal as a multiple, let's write the goal first and then I'll explain. So we'll have, our goal is that A to the K is congruent to B to the K. Well, A to the K is congruent to B to the K mod M. Alright, so that's our goal. Now let's translate what the goal is. And then see if we can make use of what we have. What we have is that B minus A is a multiple of M. B minus A is K M for some integer K. We have that, that's a given. Now let's see what our goal is. Our goal is to show that, this is the goal, let's keep that in mind. The goal is that to show that b to the k minus a to the k is a multiple of m. That's our goal. Well, let's observe. Let's pay attention to the expression b to the k minus a to the k. There is an identity, it's an algebraic identity that says b to the power k minus a to the power k equals to b minus a times b to the quickly consult the notes here. So there is an identity that says that b to the k minus a to the k is b minus a times a to the k minus 1 plus a to the k minus 1 plus a to the k minus 2 times b plus a to the k minus 3 b squared plus dot 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 and then a squared b to the k minus 3 plus a b to the k minus 2 plus b to the k minus 1. When I was just trying to recall this property, I was saying it in a different order, which started as b to the k minus 1 plus a b to the k minus 2 plus and so on up to a to the k minus 1. That would have been the same identity. But this is what I've written in the notes that are accompanying the video, so we'll go with that. So this is an algebraic property. The audience can verify by doing the multiplication that this will actually, this right hand side will actually turn out to be the left hand side. So notice that b to the k minus a to the k has b minus a as a factor. So b minus a is a factor of b to the k minus a to the k. But notice that m is a factor of b minus a. So conclusion is that m must be a factor of b to the k minus a to the k. You can write this strictly by just plugging in b minus a into the equality that expresses b to the k minus a to the k as b minus a times some other polynomial. So if you plug it in there, if you replace it, if you substitute b minus a, and you get km. So b to the k minus a to the k is a multiple of m, thus accomplishing our goal. So we're done. Proving property 4. This was property 4. I forgot to make the change there, so better late than never. The audience will be asked to establish this identity, this algebraic identity, using mathematical induction. Now, let's take a look at a summary of the proofs that were done on the board. I will run through the notes. The audience may pause to see those details, which are also part of the corresponding handout to the video. So very quickly, the audience pause. You can pause the video. So here's a summary of what went on in our proof of 2. We wrote the meaning of each of the hypotheses by the definition. We did the case of adding the two equations to obtain the first one of the properties, and we also did the case of subtracting the second equation from the first one to get the second property that's summarized right there. As far as proof of 3 was concerned, we had our hypothesis, we know what we wanted, and we proceeded. So we wrote what our two hypotheses meant, and then we multiplied both sides. We did our algebra as shown in this set of details, which is exactly or close to what we did on the board. And then our conclusion was reached. Next, we dealt with property 4. The remark is that assuming our given condition is congruent to B mod M with k a positive integer, we will accomplish proving that a to the k is congruent to b to the k by concluding that b to the k minus a to the k is divisible by m. So we employed our identity, b to the k minus a to the k is b minus a times this long polynomial. And then we lined up the meaning of a being congruent to b mod m, meaning that b minus a is a multiple of m, or divisible by m. And then we realized, we made mention that b to the k minus a to the k is in fact also is divisible by m, or a multiple of m. So we reached our conclusion. So the detail that's missing right now is proving that this is in fact true, in fact holds. All right, now let's go back to equality very quickly. So suppose we have a equals b. So suppose a equals b and c is not equal to 0. So when we deal with equality, if we divide both sides by c, we still get equality. This is a property of equality. Now, a natural question to ask is whether if we have a is congruent to b mod m, then we will get a over c is congruent to b over c mod m whenever c not equaling 0 divides a and b. Well, let's take a look at this congruence. We're often a counterexample. That's not really going to happen in general. So you have 2 is congruent to 6 mod 4 because 6 minus 2 is 4 and 4 is divisible by 4. But if we were to say divide both sides of this congruence by 2, divide both sides, on the left hand side we would get 1, on the right hand side we would get 3. But notice that it is not the case that 1 is congruent to 3 mod 4 because 3 minus 1 is 2, it's not divisible by 4. So unfortunately, there is no direct analogy in congruence to this property of equality. Do note that there is some property of congruence that could be analogous to this. It's just not as it's not as simple as our previous 3 properties. It goes as follows. Let m be a positive integer with m not equal to 1. If a is congruent to b mod m and c distinct from 0 divides each of them, a, b, and m, then a over c is congruent to b over c mod m over c. That you do get. Proof of this property will be left for the audience to come up with. It's simply a matter of developing your definition of A being congruent to B mod M to become that particular version of the definition of congruence. Now let's look at some examples. A couple of them we have. Finding remainders in solving linear congruences. So let's deal with example number 1. Find the remainder when dividing 2 to the 100 by 21. That is the same as asking to reduce 2 to the 100 modulo 21. So we're rephrasing number 1 to be reduce 2 to the 100 modulo 21. It is kind of a neat example because you get to apply various of those properties that we listed. So let's begin by looking at some powers of 2. Like if you raise 2 to the first, you get 2. That happens to be congruent to 2 mod 21. So if you find the remainder when dividing 2 by 21, you get 2 back. The quotient will be 0, the remainder will be 2. 2 to the second is 4, which is congruent to 4 mod 21. 2 to the third equals to 8, which is congruent to 8 mod 21. 2 to the fourth is 16, which is congruent to 16 mod 21. 2 to the fifth equals 32. What does that reduce into? Mod 21. Well, 11. Because the difference between 32 and 11 is 21, which is divisible by 21. Now let's try a couple more. 2 to the 6, which is 64, is congruent to 1 mod 21. Just notice that 21 times 3 is 63, and this is just 1 more than 63. 2 to the 7th, which is 128, is congruent to 2 mod 21. Let's take a look at this. These are the first few positive powers of 2. Let's notice that 2 to the 6 is actually an interesting one because this is the first power of 2. This is the first positive power of 2 that deals the least possible remainder when dividing a power of 2 by 21. That the least possible remainder will be 1. So let's begin with that. You have 2 to the 6 is congruent to 1 mod 21. Let's do the following. Let's raise both sides of this congruence by a power k such that 6k is as close as possible to 100. So you want 6k to be less or equal to 100, and you want k to be as high as possible, an integer. So here let's make a remark that the z we're looking for is actually an integer value. So solve for k here, just divide both sides by 6. So k is less or equal to whatever 100 over 6 turns out to be. Let me look that up here in these notes. 16.666666, etc. 16.666, etc. Okay, so we're going to have to choose 16 as our integer. Let's ignore that. Let's make k equal 16. So we're raising 2 to the 6 to the 16. That should be congruent to 1 raised to the 16 mod 21. Notice that this is our fourth property. We're applying our fourth property for congruence. Right hand side, 1 to the 16 is 1. Very, very simple. Left hand side, 2 to the 6 raised to the 16 is 2 to the whatever you get from the multiplication 6 times 16. That will be 96. You can put that in a calculator, 6 times 16. Now, if our question was reduce 2 to the 96 modulo 21, our answer would be 1, because that's the remainder when dividing 2 to the 96 by 21. But our question said reduce 2 to the 100th. So we're not there yet, but all we need to do is figure out what power of 2 do we multiply by on both sides so that that left-hand side becomes 2 to the 100th. Well, how about we try 4? 2 to the 4th. Multiply both sides of this congruence by 2 to the 4th. So now on the left we have gotten 2 to the power 100. 4 plus 96 is 100. On the right hand side we're getting 2 to the 4 times 1, which is 16. Okay. Notice that 16 is a number between 0 and 20. So it is a remainder. So based on this result, we conclude that 16 is the remainder when dividing 2 to the 100 by 21. Let's try our second example. Our second example is to solve a linear congruence. So solve the linear congruence 6x plus 4 congruent to 19 mod 9. So if you want to solve a linear congruence, if you want to solve a congruence, what you're after is x is congruent to what? Mod something. Alright, so we're basically trying to treat this as though it was an equation and we're trying to isolate x. So we would begin by getting rid of this 4 that's being added, subtracted from both sides. We can do that because that's one of our properties of congruence. Subtract the 4 from both sides, so we get 6x is congruent to 19 minus 4 is 15 mod 9. Now, how do you get rid of the 6? Can you just divide by 6? Well, if all of them are divisible by 6, then yes, divide by 6, divide by 6, divide by 6. But we don't have that. 15 is not divisible by 6. Neither is 9. Notice that we can, while we cannot get rid of the 6, we can get rid of a little bit of it. We can divide everything by 3 because 6 is divisible by 3, 15 is divisible by 3, 9 is divisible by 3. So by our fifth property, we can divide everything by 3 and get a new congruence. Notice that the new congruence is no longer modulo 9, but rather modulo 3. (15/3) becomes 5, and 6/3 becomes 2. So right now we have that 2x is congruent to 5.3. We really want to have a coefficient of 1 for x so that we can claim that we have isolated x completely. Now the next task here is to figure out how to make this a 1. Let's make one comment here that if we were looking at 2 and trying to reduce it mod 3, you get 2. What I want is a remainder of 1, so this is not going to work. How about we try another multiple of 2, like 4? 4 is what? Well, it's congruent to 1 mod 3. Because if you divide 4 by 3, the remainder is 1. Now, I can do this. I could say, well, multiply both sides by x. Just trying to explain here how you would reason out getting rid of these two. So right now, I'm seeing that 4x is congruent to x mod 3. Now, what's the point of doing this is I'm trying to figure out how to multiply here both sides by something, by an integer, so that this guy becomes 1x. And here is the key to that success. Let me rewrite this as x is congruent to 4x mod 3. So 1x is congruent to 4x. Well, I don't have 4x in here, so let's multiply both sides by 2 to make it happen. Multiply by 2, multiply by 2. So we get 4x is congruent to 10 mod 3. Oh, notice x is congruent to 4x, 4x is congruent to 10. By the transitive property for congruence, then x is congruent to 10. You could say by the transitive property. Okay, one last detail. Let's observe that we can actually reduce 10 mod 3 . Reduces to 1 mod 3. So x is congruent to 10 and 10 is congruent to 1, then x is congruent to 1. Again, by the transitive property. So x is congruent to 1 mod 3. Okay, so we're done. This was our goal. Isolate x, we have it. Notice that there is another way in which you could write this result, this solution. You could say, okay, x minus 1 equals to 3k, where k is an integer. So here you let k be an integer, you get a solution. So k runs through the integer, so there are infinitely many solutions in this equality. So if you want, you can isolate x completely. So x is equal to 1 plus 3k, where k is an integer. So that's sort of like the set of solutions to this congruence. All right, let's quickly summarize the two solutions. So I'm going to run through the document. The audience may pause the video to see the details that are in the document. So these are our proofs. We're done with that. So these are our two examples. So here is our solution to the first one. We used our powers of 2. Realizing that it is that one, that's going to give you a remainder of 1. Very convenient. This is kind of a key. You're trying to solve it, you're trying to reduce a power of a base modulo m. You want to try to find a power of the base that gives you a remainder 1, and then from there construct head towards your solution, towards your remainder. A little summary of what we did. We needed a k such that 6k is less or equal to 100, and k is some integer, some positive integer. We found it to be 16. We raised both sides to the 16th power. We got this partial result. All we needed was to multiply both sides by 2 to the 4th to complete our solution, our finding of the remainder when dividing 2 to the 100 by 21. So there is our result. Now let's summarize our second solution. We got rid of the 4 in this congruence. Then we got rid of as much as we could by dividing every member of the congruence by a common factor, which in this case was 3. we got a new congruence, and then eventually we made our remarks. One of our remarks was that x is congruent to 4x mod 3. The transitive property gave us that 4x was that x was congruent to 10 mod 3. And then one last detail was to reduce 10 itself. So reducing 10 modulo 3, we got 10 is congruent to 1 modulo 3. Transitive property gave us this solution. We rewrote it in a different way, and that completed that solution. So now we have some exercises for the audience. First, reduce a huge integer modulo 17. Of course, it's when you have to try to deal with it with division. We leave it to the audience to come up with the best possible solution to the problem. We were thinking of long division, but maybe there is some quicker way of getting that. Our second exercise, let me fix that. That is supposed to be 2 to the power 2013. Let's fix that. So find the remainder when dividing 2 to the power 2013 by 15. One of our examples is going to be useful in solving this particular exercise. Our third exercise is to go ahead and prove that the set of order pairs consisting of integer entries such that the set of order pairs A comma B, where A is an integer and B is an integer, such that A is congruent to B mod M, and being a positive integer not equal to 1, then that is actually an equivalence relation. Two more exercises for the audience. The fourth one, to use mathematical induction to establish the algebraic formula we used to establish our property 4. And finally, we have the audience prove our fifth property, which says let M be a positive integer not equal to 1. Prove that if A is congruent to B mod M, and C different than 0 divides each of A, B, and M, then A over C is congruent to B over C mod M over C. This concludes our lesson. That's all.